Good morning, good afternoon, and good evening. My name is Whitney, and welcome to our first Media and Entertainment webinar of 2025, Lessons from the Field, Designing High-Performance Broadcast IP Networks, hosted by Ryan Morris and Gerard Phillips. You all have asked questions, and they will be answering as many as they can get to today. Without further ado, here are your hosts, Ryan and Gerard.
Hi, how you doing? How are you doing, Ryan?
Doing all right, thanks. How about you, Gerard?
Yeah, good. It's weather is chilly, but that's very British. It's a little bit rainy sometime. But yeah, pretty good. So guys, thanks so much for joining. As Whitney says, we've had an awful lot of questions. We are going to try and answer as many of these as we can, but we're also going to try and answer them in a reasonable amount of depth. So if we don't get to all of them, we are planning to try and deal with that by either recording some extra content or by providing those as written answers. But we're going to have a good go at getting through as many as we can. So if there's questions you'd like to ask that we haven't covered, or subsequent questions from answers we have given, please do feel free to put something in the Q&A. We'll have a good go at answering those, or we'll do that after the event as well. And let us know what other subjects you'd like us to try and cover in subsequent webinars. We've covered quite a lot of stuff so far: PTP, architecture, security, basic design principles, NAT. There's a lot of there's a big audience for this stuff, and what we'd like to try and do is understand what you guys would like us to cover next. So please use the chat or the Q&A rather, to potentially let us know what you'd like us to do beyond this one. So yeah, Ryan, I think you've got the first question, right?
Yeah, thanks, Gerard. So the first question is from Vivek, who would like to understand switch models and network orchestration layer for 2110 systems and IP workflows. So like, what kind of platforms do we recommend for these kinds of systems, and why? So Gerard, you want to take that one?
Yeah, sure. So yeah, platform choice is a good one. It's one of those things that you're best doing with your SE, perhaps your system engineer. You kind of talk to your network vendor and have a conversation about the sort of scale that you're looking to build and the feature set you're looking to build, how you're wanting your workflows to operate. In terms of we're going to talk a lot about different choices and architectures. One of the things that's worth mentioning is the different multiple different platform support. So if you take a look at this is a slide that kind of describes a typical set of Media and Enterprise 2110 live production switches in different families that work really well in systems that we've delivered all over the globe. And what you'll see is it splits into two kind of major families. There's the 7800, the 7500, the 7280s. These are deep buffer, high performance, high table size, high scale switches. They're the sorts of families that you're going to use to gain the absolute maximum performance out of your system, maximum scale. You can build a system anywhere from 10,000 to hundreds of thousands of multicast flows, many thousands of endpoints, PTP boundary clocks operating perfectly at that scale. And then we have the kind of lower cost, and as you might imagine, therefore a lower feature set, typically lower scale, typically is the 7050 X3 range. And in the same family, actually, some of our 720 XPs, which are the 710s, they're all standard buffers based. They still got good table sizes and good kind of policing scale, etc. But they don't have the same capabilities in terms of scale as the deeper buffer Jericho series. And so I personally think that you can gain, you've got to choose the right devices for the right purposes, and that's what your SE can help you with. They're both incredible value, in my opinion. If you need to get the absolute max out of these things, then the biggest, which is 7500, 7800, 7280s, they will enable you to get high value by absolutely maximizing their use. If you've got a lower density system, then the lower cost switches, they provide value for money in that space, right? So it's just a different scale point. often actually, but there's also nothing to stop you from mixing and matching in those between those ranges. So if you need a deep buffer switch at the core because you need an absolutely massive scale at the spine level, that's fine. If you want to use the lower cost 7050 boxes at the edge or the 720s as audios, that's also fine as well. So Ryan, what about, can you answer the SDN part of this question?
Yeah, sure. So I guess from an orchestration perspective, if we don't want to rely on dynamic multicast, IGMP and PIM and those kinds of protocols, and we use such as something like MCS, Media Control Service, to orchestrate multicast flows in a network, then we want to get the most out of that orchestration. So policing the flows as much as possible and creating access lists on a per SG, on a per multicast basis. Then there are some platforms, like Gerard mentioned, that you mentioned that are better suited for these kinds of applications, such as pretty much anything on the sheet here that will have an R3 in it, essentially. That means it'll have higher TCAM, higher ACL scale, higher multicast scale, and higher policer scale as well. And if you, again, want to use deploy a Dante network, any of these switches will do, including the Campus 720 XPs. Perfectly fine for that application.
And I'll just throw in there the 710p, which is a little fanless throwdown type box. So super great for like a quiet audio room, but completely capable of operating in a 2110 AES-67 Dante type environment.
Cool. Thanks, Gerard. The next question is from Tim. What is essentially the most affordable switch and PTP clock source for a smaller SMPTE 2110 network?
Yeah. Okay. So the answer here, I mean, you've seen some of the models that would work. The answer here depends on the details of that small network. I mean, for example, are you building a lab or are you building a small production environment? You can go anywhere from the 710, which is that little box, all the way through to 16 line cards of 36 times 400 gig, absolutely huge. So the kind of to get to the most affordable switch and PTP clock source will entirely depend on what you're trying to build. But any of the switches that fit your requirements are gonna build you a well-functioning and the same functionality at any scale, really. The kind of how you choose to build the system is also vital. Do you have that PTP architecture slide, Ryan?
There you go.
Yeah, that one. So, I mean, this is what a typical PTP network looks like. Now we're talking here about, it's a red-blue network. You've got multiple spines. It's got a bunch of leaves on it. In general, we think about distributing PTP from the top down because it makes it easier to think about. And in that particular case, in this design here, actually, it's a pair of 7050 SX3s. So you've got 48 times 1025. You could actually, if you wanted a small system, that pair of switches on its own would be a perfectly valid 2110 PTP capable system. You can feed the GMs in through GigE or 10 GigE, depending on what your GMs happen to be. And then you've got 48 minus whatever you've attached your GMs to is worth of 10 or 25 gig endpoints. Now they could be, they could be the muons, they could be SMPs or neurons, or it doesn't matter, right? And what you've built there is a very small, perfectly formed 2110 stroke PTP system. Now, in terms of, if you want to, we typically show these architectures with a distribution layer. There's nothing to stop you from folding that distribution function into other parts of the network. If you've got spines which are 10 or 25 gig, then you can deliver the PTP straight into those spines. It's fine. Have a little bit of think about how you're going to architect it. Talk to your SE again. They can help you. It's perfectly easy to think about those PTP switches as actually the spine layer of your management network. So imagine a bunch of other 1 gig switches hanging off those PTP distribution layer at the top. And what you've got then is you've got a network which is functioning providing two functions for you. It's giving you PTP distribution and it's giving you a management layer to connect in your broadcast controller or your monitoring system or your MCS, SDN orchestrator, whatever it happens to be. So you've essentially saved yourself a spare set of switches. And it is possible sometimes to use the leafs. This works better in a purple architecture where where the spines are not defined as being red or blue. But you typically still have a red leaf and a blue leaf. If you connect those guys together, so you've got some local connectivity for BMCA between the GMs to happen, then the GMs could quite happily be sat on an audio leaf, for example, one on each audio leaf, and then connected into your Purple network. I think that probably covers. Does that cover that question, Ryan? Did I miss something there, do you think?
No, that's perfect. Thank you.
Okay, so next question from Fred. I have an existing AES67 network running PTP version 2. How do I integrate it with my new 2110 network?
Yeah, so you can really just, if you want to integrate with your 2110 network, you can, using this kind of using the same topologies we had before, you can really just uplink your AES67 leaves either to one of these leaf switches here, or you can integrate it, you can connect it directly to your spine switches as well. And the beauty again of multicast is that you can forward any of those flows anywhere, depending on who's requesting them or who's being triggered to actually forward those into your across your network. Now, very oftentimes we see customers wanting to integrate AES67 networks into 2110 networks, but also in with some Dante networks as well. And Dante, of course, is PTP version, PTP version 1. Oftentimes, they also do support, of course, PTP version 2. But oftentimes we still do see PTP version 1. So sometimes this becomes a requirement as well. So integrating a standard 2110 network, another AES67 network, and a Dante network all on the same fabric. And we can, achieve that with typically a command called PTP v1 forward. This is supported across the majority of our boundary clock, the majority of our switches, where if we want boundary clock running, PTP version 2, and we also want PTP version 1 running simultaneously on the same interfaces. This is supported on a number of switches. But in the event that, whether it's from an Arista or a third party where PTP v1 forward is not supported. So again, what V1 forward means is we can forward V1 again and V2 traffic together on the same V2 enabled interface. Then we can always add, like say an extra link between a couple of the switches that will be used strictly to carry, say the Dante traffic and the PTP version 1 traffic. You might have to play around with some spanning tree settings to facilitate that. But that is a setup that has been, tested, deployed at scale. So there are always solutions for integrating an AES67 network with a 2110 network, even if V1 is enabled as well. Now, Gerard, what if we want to integrate these kinds of networks together, but maybe there are some devices that have different domains in there. So some devices are set for domain 100, some are set for domain 120. What do we do?
That's a classic. That's been a classic problem up to now, right? So for example, Dante, AES67 mandates domain 0, right? So if you're building a 2110 system which is using true 100% standards compliant AES67, you would have a problem because those guys are going to want to lock to domain 0. So I call this PTP natting. It's not really the right way of talking about it. Actually, we officially call it per interface, PTP per interface domain configuration. I think we call it domain numbering. So yeah, so we've recently introduced this feature. You can see it 431.0f, and it allows us to. I do think of it as natting. So it allows us to have a device, for example, the facility border router on the right, which is running in domain 100, and it can connect to other stuff through a boundary clock, which is at domain 100. That's absolutely fine. Or you can enable a port or port by port. You can enable port by port to accept and send the announced messages, essentially serve different domains. So in this example here, we've got OB1 is in domain 110, OB2 and 120, OB3 and 130, and we can now accommodate that. And so this is a use case, a facility connecting to a bunch of OB trucks. They don't want to reconfigure their PTP. That'd be an absolute nightmare. They'd have to configure every endpoint. You can do that now, either at the facility border router, or if you are a truck guy and the facility didn't have a facility border router that's an Arista that can do this, you could do it in your truck and configure only one place, but essentially enable yourself to connect multiple domains together. Where are we going next? Did you want to add something to that, Ryan?
No, that you covered it. That's
okay,
good.
Cool. Yeah. So what was the next question? So the next question, I think, is Bryce. Bryce is interested to learn more about the use of aggregation switches in a spine and leaf topology for entertainment type venues. Is it still helpful to route edge switches directly to a centralized core switch in general, or is aggregation a good design path for high bandwidth media, specifically 2110 streams?
Cool. Yeah. So if we go back to this drawing here, the typical, this really is a very typical SMPTE 2110 topology. Some will have single spines, some will have dual spines, some will have quad spines. But I encourage everyone to go on to arista.com and look at the UCN Universal Cloud Networking architectures, and we have different types of reference architectures there. Some are going to be a layer 2 leaf spine, some are going to be layer 3 leaf spine. We typically see for these kinds of 2110 flows layer 3 leaf spine, where layer 3 between the leaf switches and the spine switches, and very often, but not exclusively, but very often we see L3 to the endpoints as well. It's really important to think about these kinds of topologies and how they function with multicast specifically. Layer 2 may not always be the best idea for all types of architectures, but for certain ones, like say audio deployments, and audio only, layer 2 is perfectly acceptable. But once you start getting into once you start getting into 2110-20 video, you want to go to layer 3. And so I encourage folks to look at, the layer 3 leaf spine designs, take advantage of the unicast routing protocols with multicast. So you have your PIM sparse mode, or you have your MCS there as well, because routed environments are what we very often recommend for these kinds of video deployments. With layer 2 multicast, so like, for example, if these were layer 2 links between, say, the leaf and the spine, we would most likely be getting multicast flooding up to an IGMP querier. And that would be uncontrollable, really. That's just how multicast works in layer 2. We flood the querier, which is just not good when we're going to be routing thousands of signals. It's just undesired bandwidth and undesired distribution of multicast flows. Now, if we want to get between, say, different zones, for example, or if we want to get to maybe a cloud somewhere, or just out of a specific facility, yeah, you can include another upper tier above the spine switch, is kind of like where the PTP distribution switches here are kind of connected, and have that be almost acting as a border leaf that gets in and out of a specific facility. And we've seen those very often for SMPTE 2110 systems. But again, for these kinds of workflows, look at the UCN architectures. We have many guides and reference architectures on arista.com.
I think one of the things that's worth saying or adding, Ryan, because that was a great answer, is that one of the great things about IP is that live production can leap onto this massive technological wave, ride the wave, get this amazing technology, get this amazing capacity and throughput. But the thing we have to do to enable us to continue to do that is to build our media networks in the same way as enterprises and the data centers are building their networks. And so this kind of move to leaf and spine type architectures is exactly what every single one of these absolutely huge data centers is building. And so leaping onto the back of layer 3 leaf and spine, ECMP, BGP, these are the things that enable us to continue to be using the same technologies that are being democratized, is that the right word? But price per gigabit and gigabit per watt being driven down all the time is kind of where we want to try and get to, yeah.
Cool. Thanks, Gerard. Next question from Matoki is kind of just along this topic as well. How should we respond to troubleshooting? How should we be troubleshooting these kinds of both L2 and L3 network designs, Gerard?
Yeah, that is a big old question, isn't it? So I'm gonna throw in a few little bits and bobs. So what I'm gonna do is I'm gonna highlight that there's been a series of really good multicast webinars that Ryan's done one, the TAC team have done some. So we'll stick some links in at the end, so you can go and rewatch the multicast webinars. And these are places where you can find an awful lot of debugging tools and methods. But essentially, if you're looking at kind of layer 2 multicast problems, then you're going to be looking to see if you can work out, is the query functioning? Are the endpoints appearing in the snooping tables as you're expecting? You can always mirror traffic and TCP dump that traffic. So if you need to see exactly what multicast is flowing into a port, you can typically do that on most of our platforms, will enable you to mirror that to the CPU and then to TCP dump that. So you've got pretty much first-hand knowledge of what's coming in and going out. Often these problems are about the source not necessarily being configured properly or not being configured as you expect. If you're getting into layer 3, then the first question is always going to be, is your TTL set up to be the wrong thing? I mean, that's like having the wrong S, having the wrong source IP defined, or the wrong multicast group defined, or the wrong TTL is almost certainly the first thing that I would be looking at these days. For layer 3, you've got a lot more visibility, actually. You can see what the MROUT table is telling you. You can work out whether we've seen the flow. We can look in the MFib tables, which is telling us exactly what we're trying to connect together. That gives you a really good view of when the flow was seen last, whether we're still seeing that flow. So yeah, we can't deep dive into this one, I'm afraid. Maybe we will review what's in the multicast webinars, and maybe we can do another one on that. But I would say have a look at those multicast webinars, because there's an unbelievable amount of data in there, which is really very useful.
Yeah, Gerard, there really are a series of very useful commands. Show IP IGMP snooping groups, show IGMP groups, show multicast fib, IPv4, looking at the same thing from an MCS perspective. And, some other commands that folks may not know about is you can actually also modify, TCAM on some of the Jericho boxes, the R series boxes, to actually show what the bandwidth is of a per S on a per multicast basis. So you could say, I want to look at, show multicast fib, IPv4, SG rate counters or something along those lines. And I'll tell you in human readable terms that this flow is 1.6 gigabits per second. So becoming really familiar with the commands in both L2 and L3 mode is just paramount here, because very often you will have a mix of those in your systems. And checking out those TAC webinars or some of the webinars that I did in previous year would be a good place to start.
Right. Douglas has asked a question live. He says, you said layer 3 is the endpoint. Does this mean the endpoint is running OSPF, or are unicast routes manually configured? Can we speak a bit more about that? I think that's a good one to pick up, actually. What do we mean by layer 3 to the host?
Yeah, so it'll be a routed interface. Most often we select most likely these endpoints will be /30 endpoints. They won't form OSPF adjacencies or BGP neighborships or anything like that, but the routes will still be redistributed into the routing protocol, and you'll need that in case some of those devices are going to be managed in band, or if they have to communicate with the registry in band as well. So whether the broadcast controller is managing them in band, or if they communicate with the registry in band, you'll need that unicast routing protocol there. And again, by routed there, I mean, directly to the endpoint, a /30 on the interface, mainly just because some endpoints don't support /31s. I think /31s would be great because it's much more efficient than /30s. But that is, just put the interface into no switch port mode and assign an IP address directly on that interface.
Thank you.
Yeah, sure. So the next question is from Kevin, Now that IP systems have been around for quite a while, what has been the biggest change in the design or deployment of these systems, Gerard?
Yeah, that's a great question. Thank you, Kevin. And it doesn't surprise me to get a question like that from you. So thank you very much. Be good to catch up with you at some point. Yeah, well, okay. So yes, IP's been around for a while in terms of 2110 and 2022-6. There's in my opinion, there's been a lot of big change. I think the biggest change, I'll name some of the biggest changes, I think. So scale, we are seeing some systems that are being built now that are, well, as I mentioned before, right, hundreds of thousands of multicast flows, thousands of switches, hundreds of thousands of endpoints. These are systems that are being built at a scale that SDI was never built at. And these changes have kind of really helped broadcasters to achieve the flexibility and the benefits that IP has always promised, right? Native IP connectivity end to end, with the ability to connect anything you could ever want to connect, anywhere you could ever want to connect it. So remote production, distributed production, hybrid production, you name it. Some of the biggest broadcasters on the planet are now reaping the rewards of that connectivity. With the connectivity and the scale has come the need for lots and lots of thought about security, segmentation, bandwidth management, visibility, failure domain sizes. How do you segment these networks so that you don't have a single big disaster if something goes wrong? But in general, these when you get to this scale, these networks are being designed by the broadcast guys and with really smart network guys as well. So a lot of these challenges that would have appeared really quite enormous 5 or 6 years ago are being dealt with almost on a daily basis. With that scale comes the requirement for some form of SDN. So SDN is now commonplace. I would say, along 5 years ago, SDN was not abnormal, but you wouldn't expect to see it in very many places. Now I'd say the majority of systems are now multi-switch, moving away from monolithic, and SDN is basically not a prerequisite, but a strong recommendation, and that's both for bandwidth management, for giving you better visibility. Sometimes you get better performance, and the MCS gives you an amazing set of performance, and security, segmentation done at the logical level. So stuff only going where stuff should go to, endpoints not being able to demand flows that they shouldn't be getting. So lots more SDN. Purple networks, you bring it up in your question, they're out there. I don't see a huge number of purple networks, but where they're being built, they're working well. They give a bunch of pretty cool benefits. You can think of the redundancy model as being a lower cost redundancy model. You can build a kind of a spine plus one model rather than a spine plus two model. So you can save yourself a little bit of money. You can build yourself a more flexible resilience model in the sense that you can make a choice about if you lose a link or a spine, whether the flows on that are going to be no longer -7 or -7, but no longer diverse. So you can, there's a bunch of choices. Do you have more flows or less flows? Do you have more resilience or less resilience or more redundancy? I suppose I should say. So purple networks, we're seeing more of those. But I personally, I'm not seeing a huge number more of those, but they're definitely being built.
Gerard, on the topic of purple networks, it's also important to have to support the path diversity as well. So you not only need an orchestration system, you need a really smart orchestration system to ensure that you maintain the redundancy that you just kind of implied here, to make sure that the red and blue flows don't take the same spine and create a single point of failure.
Exactly. So in a red, blue, amber, blue network, you've built a system which has got diversity built in because you've got separate, not quite air gaps, but conceptually air gap systems. So I agree. So you're asking the SDN to do more harder job, but you're also need to make sure that SDN is designed in such a way that it is now not your single point of failure. Because the -7 system with red blue gave you with separate orchestrators for red and blue gave you that kind of extra level of protection. What else is happening? We're seeing the move to many more software solutions, starting to leverage some of the standards that are being used to connect AI together. So quite a lot of RDMA, Rocky V2 starting to emerge. That's pretty cool. Again, that's riding the wave of technology. So I'm really pleased to see that. And so then your question is, am I going to run my Rocky V2 in the same network as my 2110, or am I going to build it in an AI fashion with a front end and a back end network? These are all great questions. I'm not sure that we as an industry as a media industry have kind of concluded that one, but we're on that path, which is pretty cool. And then I would say, actually, last but not least, absolutely not least, I would say this is the game changer, is automation, network as code, the removal of human error when it comes to configuring networks, changing, adding services, adding tenants, adding endpoints. This ability to kind of consider the network to be something that is defined by software almost, rather than by human beings typing CLI. So it enables you to build really complex networks following models and templates, where you can build a more software approach, an agile approach, where you have revision control of your source. You could rebuild it if your network burnt down. There's a lot of benefit in there, and having automated it, you're in a place where you can already start to automate the testing of the network, because we know what the network's supposed to look like. We can automate the testing of the network. So yeah, I would say the biggest game changer right now is automation of the network.
And on that note, if we can put in the chat link, or the link to Arista Validated Designs AVD, for other people here to just copy and take a look. We have some very good abilities there to provision M&E networks. So just take a look in there. I think it's someone can post the link in the chat, I think.
Yeah. So before the next question, Ryan, I'm going to take the opportunity to say we've got some great questions in the Q&A. I've tried to answer one or two. My colleagues are answering a few. If you don't get your question answered, please don't let that disturb you. We'll get to those offline. We may actually use if there's a really great one, we may actually use that in a separate recording, perhaps. But so keep questions coming, and we will do our best to answer the ones we can, and the ones that we don't answer, we will answer offline or some other way. So I'm going to ask you the next question, Ryan. So what is the best way to handle exchanging multicast traffic between different zones and sites? So in the previous question, I suggested that some of these systems are enormous. And one of the things you want to do when these systems get enormous is potentially to segment them so that you don't have enormous single failure domains. So slicing these bigger systems up into smaller networks makes perfect sense. Now, if I've got a bunch of smaller networks, or I'm looking to connect different facilities or even different organizations, what are the best ways of handling that multicast exchange between zones and sites?
Yeah, so I think finding a switch that will be able to perform twice multicast in that, for example, it's really important. Site A may have its own set of address schemes that it abides by, and site 2, some remote site, may have a completely different scheme, or there might be there might just happen to be some overlaps, right? And they want to be able to exchange those multicast flows. So what's important is to be able to create almost like, if this is just a very small 2110 network, we have this camera, we're sending this to the switcher here, fine, using 239.111 from 1234. We also want to be able to send that camera to some remote site somewhere else. So we have to send that to possibly a NAT service leaf. And the goal of this NAT service leaf is, as everyone can just imagine, is to perform NAT capabilities, to do twice NAT. So what I mean by that is you're NATing the source address and you're NATing the group address. Now, there might be some challenges there just from the perspective of, the broadcast controller needs to be able to understand what it's NATing from and to, possibly, and it'll have to create SDPs with the new addresses. But, this has been done today. This has been deployed today, and this is the model that we very often see when you're going between multiple sites, introducing, again, a NAT service leaf. So I have two questions here, Gerard. Like, who would route to this NAT service leaf, and then who would perform the NAT function on there? Because we probably want it to change at some point. The multicast addresses to change to be configurable and not necessarily static all the time.
Yeah. So I mean, you look at this network design, and it's a leaf and spine, right? So it's a multi-switch network. So it's in the zone of needing or having a recommendation to have some sort of SDN, something that's orchestrating the flows. So it becomes quite natural that the thing that is routing stuff to the NAT service leaf is the SDN. So you've got a broadcast controller somewhere. It's talking to the SDN, to the orchestrator. It's got a concept of service chaining, for example. So the broadcast controller says, well, I need to send this camera to that remote site, but I know that if I need to do that, I need to introduce this NAT service. So it will, it should create that kind of service chain of delivering the camera to the leaf. So that's your first part of the question. And then how do we get the NAT done? Well, do you know what? That NAT is pretty much just another device in your media network. And the broadcast controller is already going to be setting up cameras and receivers and audio boxes and processing that's essentially an IP in and IP out. Well, the NAT is just another one of those, right? So you're delivering the S, G that the camera has to a port. The broadcast controller or the orchestrator has been told where to deliver it or knows where to deliver it because it's a virtual endpoint, if you like, at this point. And then the broadcast controller tells the switch that's got the NAT function to do that NATing between this port and that port and change the incoming S, G to that S, G and maybe the source and destination ports as well, whatever it needs to do. So yeah, does that sound good?
Sounds great. Now, if you want to also exchange multicast within, say it's the same organization on the same campus, but within the campus, there might be different 2110 zones, we'll call it. Well, there is support for that as well, where maybe multicast NAT isn't needed. And, essentially we want to be able to facilitate this through a multi-zone approach, which would look like this essentially, where you have your different zones, your 2110 zone 1, 2110 zone 2, 2110 zone 3, being managed by, say, MCS, as acting as, again, the orchestration system. You'd have an MCS within each of these zones. And we want to be able to route flows from, say, zone 1 to zone 2. Now, this again comes back to almost like looking at the UCN architecture, layer 3 leaf spine, and the aggregation, and also from the aggregation question that was asked earlier, you would add in, say, these IGMP and PIM superspines up here, and those would really act as the border again between all these zones. So your broadcast controller can essentially say, I want to take this flow and I want to route it up to this superspine. And then I want to bring it in to zone 2 and route it to a specific receiver. So it's kind of almost like a tie line in that case, really. But it's using very cool new features, MCS lists feature, which we'll have documentation for. It's in EFT right now and GA very shortly. And another very cool feature, which we can go into a bit of, maybe a bit of detail on, called IIF aware IGMP host proxy. So if you go into the lists, imagine like a logical bundle of layer 3 interfaces in MCS where a broadcast controller says, I want to manage this bundle of interfaces. Just call it, a boundary interface or a list of interfaces. And MCS manages each of those interfaces independently. It manages the bandwidth on each of those, again, independently on the receiving side and on the sender side. But taking advantage of this cool feature called IF-aware IGMP host proxy, for those who may not be as familiar with that, IGMP host proxy essentially sends a multicast join from one switch to another switch if there's no PIM sparse mode between them. Okay? Now, the way IGMP host proxy works by default is it will issue a join on all of these host proxy interfaces for everything that exists in the MFib on this switch. But Gerard, like, what's the problem? What's the problem if you have like 20 interfaces here, and you have 20 interfaces enabled with host proxy, and you have an MFib that's really, really busy? Like, what do you see as a problem with that?
Well, you're gonna result in an awful lot of joins for everything that exists, right? And
Yep.
on every interface with the host proxy enabled. So So and they can't all be honored because they don't exist in the upstream zone. So that's probably fine. But if they do exist in the upstream zone, they're going to be honored on both links. So now you don't necessarily know where the flow is going to be, right?
And not just that, it's a complete waste of bandwidth, right? Like we
Yeah.
don't need the flow to arrive on this MCS managed spine here on both of these links. It's unnecessary. It's just again a waste of bandwidth. And that's where IIF aware host proxy comes in. So when MCS selects one of these interfaces in this bundle here to receive that multicast on, it will issue an IGMP join on only that one interface, thus managing the bandwidth between these two zones and not wasting the bandwidth by issuing a whole whack of these IGMP joins that are just completely unnecessary. So overall, you want to distribute multicast between different zones two ways. Maybe you need multicast NAT to do it. So talk to your SE, find the right switch to accommodate you based off of the density required, the volume required, and the port speeds required. And if you're going between zones, maybe within a single campus, this MCS with lists feature and IIF aware IGMP host proxy might be very helpful as well.
Just to follow up on that NAT thing. So I see sort of a bunch of different use cases for the twice multicast NAT. Twice multicast being talking about natting both the source and the destination. So the twice multicast NAT is pretty cool for kind of lines in, lines out. So if somebody is handing you a multicast flow, you probably want to agree on some common, almost a tie line type structure of S, Gs that you're going to be handed. So that kind of the ability to normalize the flow to something that you want it to be on the way in makes a lot of sense. And the opposite end of that is if you're distributing multicast out, you probably want to obfuscate your internal address space, and you probably have got an agreement that you're going to deliver a service on a particular multicast group with a particular source IP address, so a particular SCOMG. So that's kind of lines in, lines out. And then the third use case is, I kind of call it dumb endpoints, but there are other models. But essentially, it's the use case where, let's say you've got an amazing endpoint, but you don't have an automation capability for it. You don't have the drivers for the API, or it doesn't have an API, whatever it happens to be. But you can configure it manually to expect this particular SCOMG, this multicast group from this source. So if you can NAT it on the way to that device, you've essentially given yourself the ability to do the switching in the network. Now to me, it's not the way I would like to do things normally. I'd like the endpoint to be smart enough to be able to do things itself and to have the SDN just deliver the multicast. But if you need to, then that's another kind of use case for the NATing capability.
Thanks, Gerard. So another question from David here: multi-spine switches. What are the benefits of having a 2110 system with multiple spines? Is it just additional redundancy? Is it, scale? What are the advantages of a multi-spine red and blue network?
That is such a complicated question. Well, no, the question's easy. The answer is complicated. So, I mean, I don't know, 10 years ago, we were building a lot of monolithic-based systems. Nowadays, they typically tend to be multi-switch systems. And by multi-switch, I kind of mean leaf and spine. And a lot of those are single spine leaf and spine. And so you're building an extended system, but you have a limit to how big it can be. You can only be as big as the network can support with the size of spine. And there's plenty. It's super easy to sit down and work out what that scale would be. So I would say that the answer to this goes hand in hand with the kind of what I talked about earlier. The systems are getting bigger, right? So if the system gets bigger, you can fit a bigger spine. If you can see over my shoulder, I've got a 7800 poster, and it's huge. It's 16 line cards with, is it 36 times 400 on each one? Absolutely massive. Or is it bigger than that? I can't remember. I should know, right? But it's enormous, an incredible amount of bandwidth. But you have to you have, and there's nothing wrong with building a system based on these devices and have a single spine. But you may want to think about having multiple spines because you may need to do maintenance on one spine. You may not like the MTBF figures that your system gets you if you've got a single spine. Obviously, you're typically building 2022-7, so that does give you resilience if you lose a spine. But there are different, different customers have got different levels of acceptance of that sort of answer to a failure or to maintenance. There's plenty of customers who are actually, there's quite a few customers now building like an N+1 type arrangement. So if they work out they need one spine, they fit two. If they work out they need two, they fit three. And what that means is that you can now essentially, use techniques like BGP drain down, or maintenance mode, use techniques like MCS drain down, maintenance mode. You can move flows off one of them and do your maintenance, upgrade it, fit a new line card without losing any redundancy, without losing any throughput. Now, that's a more expensive way to go, but if your content is valuable enough and if your uptime requirements are strict enough, then that's a mechanism that you could use. So I would say there are lots and lots of cases where multiple spines are being used. Ryan, I am conscious that we are heading towards the end of our hour, and we've still got a few questions left. So let's hop to, can you describe some of the best practices in a network design for audio production or video production?
Yeah, so a lot of the audio systems, I think we mentioned this earlier, used to be, L2 only. Audio is obviously very low bandwidth, so we don't typically need to worry about orchestration and bandwidth saturation. So, L2 is okay. There's a lot of discovery services in there as well, taking advantage of MDNS, which is an L2 protocol. So again, L2 is just fine. But for those video systems, which we've reviewed, layer 3 is the way to go. 100% layer 3 between the switches at least, and whether or not you want it at the endpoints or if you still want the endpoints on a specific switch to be within a VLAN and then have an SVI for that VLAN, that's up to you. We see customers deploying both models. Currently, I'm seeing more L3 exclusively. So I would say, and one of the reasons for that again is, reducing the blast radius of a network. If one device decides to be decides to misbehave and floods the network instead of just distributing regular multicast, it turns into broadcast for some weird reason. You don't want this to impact other endpoints. It would only impact itself, essentially. Nothing would happen if everything is separated by a layer 3 domain. So that's one of the reasons why we're seeing more L3 approaches. So, that's what we see from a best practice perspective. And if it's a spine leaf, more SDNs, more orchestration services, like Gerard mentioned.
Nice. Thank you. Okay. So next question then from Dave. Actually a three-part question. So part one, on a local network, why is the port address mapping implemented as if it were a point-to-point address in remote sites? I think that's actually asking about point-to-point layer 3 interconnect. What do you think, Ryan?
Yeah, I think that's what that question is, and this is what we just kind of covered now. L3 directly from the interface to the endpoint to reduce the size of the blast radius. /30s are more common, but 31s would be preferred.
Okay. Then the second part of the question is pretty interesting as well. With multicast capabilities, why do you still have a unicast implementation in a multicast rich environment? I think it's
to build a multicast tree from the receiver back to the source, back to the sender, you need those unicast routing protocols, OSPF or BGP, to actually build those trees. It's called RPF, reverse path forwarding. So device receives an IGMP join, or the switch receives an IGMP join, and it's got to build that path to get back to that sender, or at least up to the rendezvous point at a minimum first, if it's a star comma G join. And that's the reason why. Multicast alone isn't enough in an IGMP and PIM world. You need those, you need the unicast routing protocols as well to build those trees. And Gerard,
Nice.
I'll ask this one. In ISO 4, why is there so much manual entry required on the initial configuration?
Well, I will point you back to my original question about automation, or the answer about automation. There's absolutely no reason why there should be lots of manual data entry. That is entirely down to implementations from different vendors. So, in a lot of cases, broadcast controllers can populate a lot of this data. So, yeah, I would say have a chat with your vendor who's expecting you to do a lot of manual entry.
Cool. Here's another question pertaining to multicast from Celine. What are the pros and cons of SSM, source specific multicast, versus ASM in a broadcast environment with or without SDN?
Okay, so if we assume SDN is not in play, then often the choice of ASM or SSM is made for us by the endpoint vendors feature support. Lots and lots and lots of audio kit is ASM. So let me just point out, ASM is any source multicast where we don't know what the source is. We don't care. We're just delivering a multicast group. And it requires, do you have a slide for that one?
Here it is.
Do you have the, yeah, so in ASM, we don't know, the endpoint requests a multicast group. We don't know what source it wants. We don't know what the source IP address is. In SSM, the endpoint requests an S, G, and requests the multicast group and the source for that multicast group. And the biggest difference is that in the case where an endpoint asks for does an ASM join, it doesn't know where the source is. And so the only way to work out in the network where the source is to use the concept of a rendezvous point. So in an ASM network, we need a rendezvous point. The rendezvous point is the place where essentially the source and destination get married. Once they're married, once the source has got to the RP and the rendezvous point, and the request has got to the rendezvous point, the traffic will be forwarded on to the right place. And at that point, once the source has finally got to the endpoint, the endpoint, the last hop router now knows what the source IP address for that multicast group is. And so it can switch from what is known as the shared tree to the shortest path tree. And that becomes, essentially that turns into an SSM join. So any ASM join is essentially turned into an SSM-like join by the network infrastructure. So if we go, there's no, I like to think of SSM as being very well suited to 2110 because the model is typically you've got a camera, it's got a source IP address, it creates 2 flows, 4 flows, whatever, but they all come from the same camera. So when I ask for a particular flow from that camera, I kind of probably know what its IP address is. I should be able to ask for the IP address and the multicast group. I think of ASM as being very good for services. So if I don't know, if lots of people need to contribute to that service, like Transparent Clock PTP, or like some of the registration discovery protocols that are out there which use routable multicast, you just subscribe to a multicast group and everybody will tell you their information about that group. So you discover everybody. It's a bit like finding a printer, right? But so in general, I would say you're not going to be able to avoid it because lots of audio kit doesn't do SSM. Lots of audio kit only does ASM. Some video kit only does ASM, right? So you're very likely to end up in a system where you've got to have both systems running. I would say it would be nice to build a network without ASM, so you don't have the complexity of the RP, but in general, you're likely still to need it.
Agreed.
Yeah. So, Ryan, what are the areas? So Michael asks, what are the areas in which SDN is critical for high performance IP broadcast networks?
Yeah, so it's a good question. So if you want more visibility, for example, like you want to know that the route was successful or the route was not successful, and if it wasn't successful, why wasn't it successful? There's orchestration systems like, again, Media Control Service, MCS, which provides all of those notifications back to the broadcast controller or back to whoever is actually monitoring those types of notifications. So increased visibility is one reason for sure why to move to an SDN. The second one is, again, it's just this little drawing here. If I want to route from all my 320 gig traffic from switch 1 to switch 2 over 4 by 100 gig links, can I be certain that I can route all of those flows? Gerard, can I be certain? Can you guarantee me that I can route all of those from switch 1 to switch 2? in an IGMP and
Well,
PIM environment?
well, there's obviously enough bandwidth if they load balance perfectly, but of course, PIM is standards-based PIM is not a bandwidth
Simper.
aware
Yeah.
protocol. So no, you can't guarantee that. And interestingly, as the size of the flows gets bigger, like 3G UHD, compared to the carrier, the 4 times 100, as those flows get bigger compared to the member bandwidth capability, then that hashing typically becomes less efficient. Yes.
Yep. So that's a big reason why we want to ensure that we can route all of the traffic from switch 1 to switch 2, and an orchestration service can ensure that. Also, if say you do get perfect distribution, 80 gigs across each of those 400 gig links, and you lose one of the flows, or sorry, pardon me, you lose one of the links, we don't want all that extra traffic to be redistributed across all of the other links, because then losing one link may actually result in you losing multiple links and even more flows that way. So,
Thank you.
Gerard, next one is on monitoring, from a question from Dan. What are the tools and best practices for monitoring, measuring, and alerting in a complex 2110 network?
Yeah, another huge question. So I mean, I guess we'd start with the quality of the data is important. I think the move, another big move is this kind of providing streaming telemetry, real-time streaming telemetry. So talking about streaming events rather than streaming state. So we stream when state changes, not streaming the state all the time. That helps you have the data more up to date and with a lower latency on getting the data and a lower processing overhead of receiving the data. So streaming telemetry is super important. In terms of tools, CloudVision, CVP can help with monitoring, built-in dashboards. Have you got the PTP telemetry overview there? You got that slide
Yep,
for me?
yep.
Right.
One
So
second.
being able to visualize data in dashboards, being able to use Arista's AQL to customize your dashboards, build the dashboards you're looking to have, being able to tie in notifications with the ability to send those notifications to external places like Slack or Teams or Google Chat or whatever is super handy. Typically, the streaming telemetry can be doesn't have to go to CloudVision, right? The streaming telemetry comes out of the switch. You can send that. You can process that as you wish. So there are many people who take that streaming telemetry and visualize it in something like Grafana, for example. And that kind of brings us on to so CVP is great. It's really good at that network stuff. Gives you an amazing bunch of features, well worth looking at. Ryan, who else is using our telemetry and what they're doing with it?
Yeah, so CVP is obviously fantastic for network engineers, but sometimes broadcast engineering folks want something that's more presentable towards, their specific workflows. And that's where, the partnerships that we've made with, Providius and Skyline, for example, are really vital in these kinds of systems, where they can get that same data, they can consume that same real-time data from the switches over a GNMI connection, for example, and process it, consume them in the same way that, CVP would, but present it to the broadcast engineering groups in maybe a way that they're more, that they are more familiar with. And that's kind of what Gerard was referencing with being able to, other parties being able to consume this real-time telemetry data. Our partnerships with some broadcast engineering vendors, again, like the ones I just mentioned, Skyline, Providius, and there are more out there, really make this possible. So you can have the, CVP for more of the network engineering teams, and you can have these other tools for broadcast engineering teams, and then they could be looking at the same data. They could be speaking essentially in the same language, as well, not having to alternate between router mnemonics and multicast IPs. They can communicate with the same data at the same time, essentially, seeing the same.
And there's loads of other stuff out there. Douglas mentions, Tim mentions TrackCount, which is a great bit of functionality to kind of have an external laptop or something that can analyze the quality of the PTP that's being delivered through a boundary clock, for example. So that's definitely the case. The EB List project is another amazing piece of actually open source kit that will enable you to analyze. You can analyze PTP and analyze the coherence of flows coming that you've delivered to a piece of test gear. So Ryan, I noticed that it is, in my world, it is now 7:01. So we are now overrunning our hour, and I don't think we want to, we don't want to, steal time from people. So I guess I wanted to say, do you have that last slide? Do you have the last slide?
Yeah, absolutely.
So,
Yep.
thank you guys for sticking with us. Thank you for providing your live questions. Thanks for providing the questions before the event. Ryan, thank you so much for your expertise and your time. If there's anything we can do to help you guys out there, please don't hesitate to reach out. There is an email address there, media-ent@arista.com. That goes to our media entertainment working group. If you've got questions or you've got ideas for webinars, or if there's something that we said that you didn't like or didn't make sense, please feel free to drop us an email there. If you're going to be at NAB, we will be there too on South Lower 4723. If there's something else you'd like to know about that we've covered in a previous webinar, we will be sure to, in the email that we send out that contains the recording of this event, we will send the links to the webinars on this slide. Ryan, I feel I've missed something. What have I missed?
Just thanking people again for all your questions.
So,
thank you, really. Couldn't have done this without all of you. Thank you.
Thank you so much. Thank you so much for taking the time and for the questions. And we'll see you at the next one. Thank you very much.
Thanks.